All right, next we're going to have a presentation by Derek Pizarro. He is a certified PG, senior product manager and principal at AST Environmental. And he's going to talk about PFAS source management using a modified clay PRB for PFAS remediation. Derek?
Thank you, everyone. Good afternoon. Thanks for joining us here at the PFAS Forum today. As mentioned, this talk is going to focus on using a modified clay for sequestration of PFAS. This is going to focus on the first injected modified clay site, as we know it worldwide, for the sequestration of PFAS. And then we'll also at the end review just briefly a couple other things that we have going on at other sites. Some are underway currently and some unfortunately didn't get underway in time for this presentation, but we can discuss some of the things that we're doing at those sites from an injection standpoint that do have relevance to what we're talking about here today. All right, so let's start with what is a modified clay. So for purposes of this presentation, the modified clay that we're using is one manufactured by Setco. Its trade name is FluoroSorb. But this starts as a bentonite clay that's modified specifically for PFAS sequestration, modified by installing a quaternary ammonium surfactant into the inner layer space via cation exchange. So this is taking a very common Wyoming bentonite that goes into a lot of different products and then modifying it for this application. So it is specific for PFAS. Though if you've worked with Setco, you've probably used their other products and other applications as well. We've also, through working with Setco, some of our partners here domestically and also in Canada, this case study will come from Canada, we've evaluated the performance of the FluoroSorb versus the modified clay versus ion exchange, different activated carbons, and also biochars. Now, the number one question we get when they hear bentonite clay, right, even at the very early design stages, is this going to swell? And I'm going to tell you, because of the modification in the manufacturing process, that it does not. We'll get into some of the things that measure that swell in a few minutes here, but I'm going to tell you on a gross standpoint in the field, you do not have the capability to measure any perceivable swell in the product. The other thing we like about the modified clay is it comes in various sizes. So if we do this via injection, we typically have two sizes available to us, a powdered and then a 100 version, but we also can step that up if we're doing, or you're doing as practitioners, a yellow iron application of this, say trenching or soil mixing as well. The reason we ended up using modified clay for the case study I'm using as an example is it does have a high absorption capacity. We can, AST is an injection contractor by trade, we can push the loadings with this product a lot higher than we can with other adsorbents that we're looking for to create an overall higher absorption capacity in situ. That includes even outpacing the absorption capacity of activated carbons of various sizes in the marketplace. And then most significantly, because a lot of sites we're finding, especially here domestically, the more that we work with practitioners such as you in the room, we're finding that a lot of these sites are not just PFAS, right? There's some other type of co-contaminant involved. If you use an activated carbon, right, it likes to grab onto a lot of different contaminants, so you end up using up that space that's available to you. In the instance of FluoroSorb, we don't have that issue, and we'll talk about why we don't in a few minutes. It's also not affected by various other co-contaminants, geochemistries, saline environments, and it doesn't react with the geology around it, so we don't have that concern. Some of these I covered on a previous slide, but I'm going to focus on the fact that the number one thing we're comparing this to, because it's what's been used the most in situ in the industry to date, is some sort of activated carbon, right? And I've mentioned some of these, just I got ahead of myself on the previous slide. But what's important to note is whether you're using a modified clay or an activated carbon, you're talking about something that's a true slurry. So you're talking about different pumps, different designs that you're using to install this in situ. So we're talking about very dense, high-capacity slurries for the absorption. And so as we go through this process, this design process, it's something that we need to understand a lot about the geology of your site, right? A lot of things that control a slurry installation in situ revolve around the geology, the starting depth, right? And then the volume you have to shoot per interval. And that those are really the primary constraints on how you come up with a design for your site. And so I mentioned earlier the absorption mechanism was a little different with the modified clay versus the activated carbons. And one of the reasons for that is, that's strange, sorry. One of the reasons for that is it doesn't have it can't be overwhelmed like activated carbon can in most settings at a reasonable dosage. And the reason for that is with the modified clay, as the PFAS absorbs to the plates in the modified clay, it chains onto itself, and actually, and you can see from that graph there, it pushes the plates slightly apart, and we're talking on the order of angstroms, so this is not field swelling, but that allows you to increase the uptake of the PFAS between these plates. So there's a very large absorption capacity, especially with the powdered version of this. And also being a powdered version of the modified clay, we can install more of that, so a higher weight percentage in your slurry gallon than you could be with even some of the activated carbons that we look at. Does it work? Well, it's going to be very site specific. So one of the things that we encourage you as practitioners is very early on in the process, not just engaging us, but also engaging the manufacturer of the product or products you're considering. And the reason for that being is you need to go through the process of an initial evaluation based upon available isotherms, depending on the product you're looking at. You also need to make sure it's deployable, depending on the way you're installing it. And then you probably need to evaluate. A lot of our clients, especially with co-contaminants, are going through a bench scale study to evaluate which product is best. And that's really important. An example I'll use later for a site here domestically where we had to use FluoroSorb with calcium polysulfide for hexavalent chromium. So in the instance of that bench test, we actually found that there was a decrease in both the calcium polysulfide treatment and the activated carbon capacity when they evaluated activated carbon and calcium polysulfide. That interaction did not occur with the modified clay. So again, go to the bench scale study to make sure these things are compatible with each other. In terms of where does this go, the next few slides focus on a McGill University study. So this is a laboratory bench scale study. Sorry, for some reason it keeps advancing my slides. I think I got to remove an automatic thing there. But we're looking at how does it compare between different common adsorbents that are used ex situ, even though you may not use all of these in situ, just from an installability standpoint. And specifically, I'm looking at IX resin, something that while there is a powdered version to date, we don't really see that being requested for injection in situ for various reasons. Sometimes revolving around cost, other times revolving around the installability of that product. And so from a comparative assessment, what can we take away from this university study? Well, we see that the FluoroSorb is very similar or better in some cases than ion exchange for the removal of the total PFAS. In terms of the long chains, it's almost analogous to each other. But we see that both outperform granular activated carbon and biochar. So we know from a ex situ pump and treat standpoint that these products on a whole have gone through long-term evaluations. We're talking 5, 6, 7, 8 years, depending on the study you're looking at. And so we know that these products are applicable in situ. The question is this appropriate for your site, and is it installable in situ? Again, I mentioned co-contaminants. In most cases, the modified clay is not affected by co-contamination. And what was interesting in one bench study that involved having a diesel product as a co-contaminant, we found that it actually increased the loading capacity between the plates of the PFAS. And part of that is, that leveraging a part of the plates, right, allows us to also absorb additional contaminants there, but we don't have the competition that we do with something like an activated carbon. So everything's going in between the plates. The site this came from, the client goes, oh, so I can solve this by installing FluoroSorb and putting diesel in the ground. We're like, no, that's a joke. Like, don't run out there and do that. But yes, in the presence of other co-contaminants, sometimes the uptake performance does increase. I'd say the number one use of these type of products is right now a PAB, usually cutting off a plume, managing a distal end, something at a property boundary. Maybe depending on the site, if you can't get to the source zone, you might be doing this outside of the source area for management. It could be even in conjunction with a pump and treat. Most of you as practitioners in this room have probably done permeable reactive barriers, slurry cutoff walls, similar applications. It's the same concept, right, whether you're injecting it or trenching it. I would note that in the injection deployment of a PAB or a PRB, you're typically looking at multiple rows of whatever injectate, not just modified clays in this application, but you need to generate contact. And the example I'll show you here in a few minutes is, when I say generate contact in situ, I know a lot of people call it a contact sport. That's a little bit overplayed in our industry, but it's really about generating enough residency time with some contaminants as well in the case of PFAS. So it's not just having the product distribute evenly throughout the geology in your site, it's also about having enough flow through time to generate that contact and residency onto the product itself. And so it's very hard to do that with one row, or extremely hard to do that with one row. 2 rows, better. 3 rows is almost always, on average, the most ideal, especially if you have high concentrations. So to rewind this, how did we get started with installing modified clay in situ? Well, this dates back several years. At the outset of me joining AST from a chemical manufacturer, we talked with Setco about possibly installing this. They'd received inbound inquiries when this product hit the marketplace, circa 2019, and a lot of it was done with yellow iron. A lot of it was being used in pump and treat systems. The question was, could it be injected? And at that time, we had the 100, which we believed was injectable, but we wanted something that was a bit more advantageous, something we could push the loadings on in situ, and so that FluoroSorb P version of this was developed, something that allows us to push the pounds per gallon in the injectate even higher in situ. So proof of concept, as I mentioned earlier, we have been installing very viscous slurries for, well, at this point, over 30 years, but we used a lot of the design and techniques and equipment that we had been using for those other products. We applied them to the modified clay here. And so we did a demonstration project here in Kentucky, and this was this wasn't quantitative, this was a qualitative evaluation of distribution of the product in situ. So this started with how much can we get in? So we varied the loading rates of the FluoroSorb 100, we varied the loading rates of the FluoroSorb P, and we also evaluated different spacings to see if the spacings based upon depth and geology would be very analogous to either a granular or powdered activated carbon. What we found was that the powdered version matched up very well with powdered activated carbon. We found that the 100 version matched up very well with granular activated carbon, all of which we'd been injecting over 20 years. So the design for these sites really was rooted in experience, and it was good that it matched up like we expected. The one thing I would note again, the powdered version of this, we can push those loadings higher than we can with the 100, which again matches up with industry experience using PAC or GAC as well. So in our demonstration test, you can see on the dip cup here on the right, there's 2 things that we as installers are looking at when working with any product, and this applies again to modified clay. The first is settling velocity in the tank. What is the energy going to be required to keep that material suspended before we inject it? Because again, one of the advantages of using systems like these is we're not dependent on using guar or other suspension agents, which you can use for some deployments, and it's applicable for some injection designs for other contaminants, specifically VOCs. But here, what is the most unadulterated way we could put this in situ? And that's what we were looking at. And so what I'm showing you here, this dip cup here comes out of the batch tank. That's about 2.5, 3 minutes of settling. So you can see in the absence of energy to keep it suspended, it will come out, right, of suspension, as we would expect. What was interesting when we went through this is the cleanup was a lot easier. This washes down well in the tanks. Everything was very easy from a housekeeping standpoint, which isn't always the case when we work with something like activated carbon or iron products. Like this just was fantastic as installers to work with. So that was kind of an unexpected caveat. And again, as we went through this, the distribution was very similar to what we expected from other installations. So reusing that dip cup thing that was pulled from the batch tank there, and this is from, on the right there, that nitrile glove, this is the 100. So this is the 100 dip cup dumped on our hand, and you can see that the product there is like a medium to coarse sand in size. So we are physically installing something with a significant % solids in situ. It is a true slurry. All right, so on to the pilot test, the case study here. This is going to focus on a former firefighting training area. They used AFFF containing PFAS. And the plume here intersected a utility corridor with a sewer line in it. That became our preferential pathway. That became the conduit and also the sink for the PFAS transecting the site. As it moved through this preferential pathway, it also impacted a swale area, and then from there it would flow either over or slightly underground towards a down-gradient river where they had variable detectable PFAS over time using the concentration limits available to them. So this whole process started as risk management. They want to mitigate, they want to do a pilot test, they want to do an evaluation, they want to move to a full-scale implementation, which they will. What we're looking at here is the primary goal was immediate PFAS reduction. So we're not going for a standard. This is how much product can you install because of the concentrations we're dealing with and what kind of reductions can we see. We're also dealing with a very high flux and variable groundwater rates, and this being located in Canada, we also have snow melt to consider annually. And they wanted something that was a passive long-term solution, right? Something that's very low maintenance, keep your O&M costs down for this. So the concept here, as we've outlined for previous slides, is this going to all be in situ. It's going to be DPT injection. And from a bench scale standpoint, they did evaluate several amendments, and they focused in on the FluoroSorb P for this installation. Interestingly enough, they are discussing using reactive core mats, which some of you in the room may know are a punched geotextile filled, in this case, with the FluoroSorb. They will use that in some other locations like the swale and up gradient towards the source. So when they approached us, they also asked us to do a bench test study. We actually, in the end, went straight to pilot after the design. They said, we just want to put something in situ and evaluate our site. So what they did do, though, was they went through both studies we had done, our partner in Canada, VEI, what they had done, and they also looked at third-party university studies as well that had gone through third-party review and evaluation. And what they focused in on was the increase in uptake, or removal in this case, of PFAS versus these GACs versus some of these micronized carbons. And what we're looking at here on the right is just from one of those column studies that we did in the lab. And what we're looking at is the bed volume contact removal here versus FluoroSorb versus GAC. This was actually the FluoroSorb 100, I believe. I don't think we had the powdered at that time. But what we're looking at is, can we overcome the issues we have with the activated carbon saturation? Are there breakthrough? Is there competitive absorption? All of these, which were going to be concerns at any site, were brought up during this process as well. And then the last piece is, can we put in a product that's going to, on a growth standpoint, manage the concentrations we're dealing with, because they were significant at this site. So they settled on the FluoroSorb P through this. Again, I mentioned this was DPT injection. We pushed this to a fairly high loading rate based upon the initial assessments we'd done with our pilot test in Kentucky, which ended up being about 3 pounds per gallon, which was effectively a 1.3% weight dosage in situ. We used 5-foot injection centers for this site. Now, again, that's predicated upon the volume of product we have to install per shot. It's also the geology of the site, which was a fill bedding material. So it does have, it's previously disturbed. It does have a lot of porosity. So we know we've got to keep the injectate in the ground. So we focused on getting centers very close to each other. And for this whole installation, we're talking about something that's 5 or 6 feet down to 13 feet below grade. In terms of performance monitoring for the site, we focused on both hydraulic response using existing monitoring wells. We also installed some piezometers and temporary wells. We also took cores, and we used a proprietary dye tracer here, which was, we call it semi-quantitative. It's colorimetric. What we can do is we can take the soil from the cores, and after we've done a calibration on it using undisturbed, unloaded soil from the site in that area, we can then calibrate a curve based upon several loadings of, in this case, FluoroSorb P, use that calibration curve when we pull the cores post-injection to come up with how much product was actually distributed at that interval within that core. And it actually worked extremely well in the field. The client was really pleased with that. And then the last thing we did was slug testing, which will take me to one of my final slides here in a second. I'll get into that in a moment. So if you're just trying to visualize this, right, from an interleaving standpoint in situ, we're trying to generate what would be a contiguous barrier if you would use yellow iron versus injection. If you haven't done this type of installation before, I can tell you on a performance standpoint for a PRB or a PAB, it works just as well, right? The performance on these, if you do your design correctly, is going to work just like a trench barrier would. What does it look like in situ? Well, here we're dealing with something that's a little bit coarser. So the picture on this slide on the right is probably a little more analogous to the FluoroSorb deployment here. That's a medium to coarse sand. On the left, we have a clay. Neither of these cores are actually FluoroSorb product. We're using a powdered activated carbon in both of these. The reason I chose that is because you can see the distribution, which again is analogous to the FluoroSorb, the modified clay product. And what we're looking at here is on the left, a true fracturing, but also because of the pressures we use, we do get interstitial disbursement of that vertically as well within the spaces of the clay or the fine silt. And then on the right, we are looking at what we call radial co-mixing, which is a physical tumbling of the formation with the product. So you get a much much more even distribution there. It actually requires higher pressures. And again, none of this can be done low flow, low pressure. This has to be done with high energy. And so here's what that installation looked like from a schematic standpoint. The bedding in the area we ran the pilot was on average about 135,000 nanograms per liter. And we installed, in most cases, at least 3 shots per DPT point, as you can see on the right, and we traced it down the sewer line. Here's some guys standing around a geoprobe in the field. I kind of threw this in here if I was running short on time, but I'm not, so I'll move through this. Most of you probably know what a geoprobe looks like at this point. And so here's what I was talking about, the slug testing. I'll wrap with this. We get asked a lot when we install, especially very, very viscous, dense slurries, is there going to be a change in hydraulic conductivity at my site? And with this product and others, we can demonstrate using slug tests before and after injection that there is a very small reduction in hydraulic conductivity, typically within the margin of error for the testing you're doing. So we could say that, can we say that we have not changed at all? We can't say that, but we can say that it's so minuscule that it does not hinder the overall flow at the site. And so here's the performance from the site. The initial reductions 4 months into this within the source area of the bedding of the utility corridor. We saw total PFAS reductions of 89% on average. Within 9 months, those had climbed to 93, and we're approaching 95, 96 at this point for total. We also weathered a high flux rapid snowmelt event. That was something else we had to account for. You can kind of see that there in the February 2024 data. There's a very slight uptick in total PFAS, but again, considering the concentrations we started with, these have come down significantly. And I'll just mention, we've got some other work going on here. I didn't have these available in time for this presentation, but we are doing PFAS and hexavalent chrome. Again, the products are compatible with each other. And then we've also done some funnel and gate evaluations at sites in North America that are, at least the one I've got here on this slide, that's a funnel and gate with a cartridge. So they evaluated different loadings within the cartridge, and they'll pick one, and then they'll cycle that cartridge out just like you would an ex situ system, except this is going to be an in situ cartridge for that treatment. But again, you can see the removal from the lead and the trailing cell in that cartridge. Again, the modified clay was highly effective in removing the influent PFAS. So in summary, we demonstrated that modified clay is not just laboratory suitable for the sequestration of PFAS. It can be injected in situ for the sequestration. Co-contamination, which we deal with on a regular basis, a lot of sites does not affect the performance of the modified clay in situ. The modified clay is injectable using conventional high-energy injection systems, which are available, and it can be co-injected with other reactants and products, as you saw from the comments on the previous slide. And we are evaluating, more than just calcium polysulfide and other iron products out there that can go with it. So that's ongoing both in our labs, SETCO, and our clients as well. I appreciate your time.
We have time for a couple of questions. I have one or two. How's the particle size of the modified clay compared to colloidal carbon, as well as the cost per unit price?
I knew someone was going to ask the cost question. And what do we all say on the panel? We always say, I was joking about this with Cameron, we always say it depends. I mean, on a pound per pound basis, the modified clay is generally less expensive than a micronized, a powdered, or a granular activated carbon. In terms of sizing, the 100 again is comparable to a granular activated carbon. It's probably highly comparable to say like Calgon's FF400. In terms of the powdered, I'd say you're probably looking at a very fine powdered activated carbon in terms of mesh sizing. SETCO may have some more details on that, but I think we're talking about something in the order of maybe 20 microns, somewhere in that range. I see Rebecca nodding her head, so at least I'm in the right ballpark.
Any other questions?
But to that extent, that's one of the reasons that for the site in Canada it was attractive to the client, was that at 20 microns roughly in sizing, that's not going to move once the energy of injection is turned off. So you are creating a true barrier.
So you would expect a similar radius of influence for modified clay and colloidal carbon?
Not colloidal carbon. The modified clay, I mean, to my understanding, colloidal carbon is typically injected under low flow, low pressure. Even moving up to, say, 15, 20, 30 microns in size, we still need to, especially at the loadings we typically need for PFAS, we are creating a true slurry. So, no, we can't do this under low flow, low pressure.
Very high pressure. Okay. Great. Thank you very much.
Thank you.